Good morning, everybody, and welcome to the second FEBio Studio webinar. My name is Steve Moss, and I am the lead software developer on the FEBio and FEBio Studio projects. In this webinar, I'll be talking about contact modeling in FEBio and FEBio Studio. Now, although contact is a bit of a more advanced topic, we chose this topic as our second webinar because we felt that we get a lot of questions on contact, and we hope that by making a webinar on contact, we can explain more about the background in FEBio and give users a lot of information on how to be successful with modeling contact in FEBio. Now that said, contact is a very vast topic, and we will not be able to cover everything that we would like to say on the topic of contact in this single webinar. So in this webinar, we'll talk more about the basics of contact, and then in later webinars, we'll do some more advanced contact topics. So to give you a brief overview of what we're going to do today. So first, we're actually going to take a look at some of the file formats that you would run into or that you would use if you use FEBio Studio. And although we covered that somewhat in the first webinar, there have been some recent changes that are relevant here. And then in particular, I want to take a moment to talk about the plot file, so the file where the results are stored, and talk about how that actually is stored, because I think it is important that people understand that there is some processing going on when the data goes from FEBio to FEBio Studio. So after that, we'll jump right into contact. We'll do a brief overview. We'll talk about some basic contact concepts, and then we'll give lots of examples to illustrate all the different contact features. So we'll have lots of tips and tricks spread out through the presentation that will hopefully be helpful in your contact modeling. So at the end, we'll do a Q&A session. Now we already have the Q&A window open, so if you have any questions, feel free to go ahead and ask them. We have several panelists standing by that will be answering your questions. I do want to ask that you keep your questions focused on the topic of contact modeling. So if you have any other questions, more general FEBio questions, I ask you to either ask them on the forum or ask them via email after the webinar. So with that said, let's get started. And so let's talk briefly about the different file formats that you will run into in using FEBio Studio. The first one is the FEBio Studio project file, and this is somewhat of a new feature, so I want to take a moment to explain that a little bit. And so the purpose of the FEBio Studio project file, I'm trying to get my FEBio Studio open here. There we go. So the purpose of the project file is basically to provide a convenient place to keep all your model files together. And you don't have to store just the model files in this project file. You can store any other file or resources that you use or that belong to this project. So you can add, for instance, text files. And so double-clicking any of these files will open up the file. Most of the files will not open in FEBio Studio, except for file formats that FEBio Studio will recognize. But you can store PDFs, so resources that you've used for creating these models, you can store in there, even videos that you make. So you can store all these things in the FEBio Studio project file. Now the file itself is just a text file. So let me show you quickly here. So this is the text file for the project file. It's just an XML formatted file, so you can manually create these files if you'd like to, but you should be able to edit most of the contents in this file directly in FEBio Studio. So you can create, for instance, new groups. We'll make a group for our rigid problems, and then you can move files into these groups and so forth. Okay, so that's the first file format. The second file format is the FEBio Studio model file itself. So that's the file that will contain all the model information, including the geometry, the mesh, the physics of the problem, boundary conditions, contact information, obviously, job information, and so forth. So you can open these files directly from your project panel here. So you just double click on them and it should open up immediately in FEBio Studio. So the next step would be, so after you set up your model, the next step would be to run the FEBio model in FEBio itself. So the way that works is, so FEBio is still an external application, as we explained in the first webinar, but you can call this application directly from FEBio Studio. So you do that by just clicking here on the FEBio icon. You can give your job a name and so forth, and then you can run this directly in FEBio Studio. Okay, so what FEBio Studio did, it created a FEB file, which is the input file format that FEBio Studio uses. And another new features that we've added is the ability to open this file directly in FEBio Studio. So let me find the files quickly here. So this was the sliding example. So when you want to open an FEB file, you now have the option to import it as a model, like the FSM file, or you can import it as a text file when you can just edit the text manually. And you can even run this file directly in FEBio Studio as well. So now I am running the FEB file instead of the model file. So in either case, when the model completes, it creates a plot file which contains the results of the analysis. Right? So here I've opened the plot file here. You can see the name of the tab. The name of the tab here is sliding XPLT. So XPLT is the extension that we usually use for the plot file, and that one contains the results of the analysis. So now that we're on the topic of the plot file, I want to take a moment to talk about an important thing that we didn't emphasize in the first webinar, and that is that the contents of this plot file is something that is completely in your control. And it's important to know that you have to specify what variables that you want FEBio to save in that plot file. It does not save all the variables that it calculates because that would generate huge plot files. Instead, you would have to do that. And to do that, you would find the output item here in the model tree. You click on plot file, select edit output, and here you have all the lists of the variables that you can plot. Okay, so for contact, you can use the filter here to filter out plot variables related to contact, and then by checking them, you will add them to the list of the variables that will be stored. Okay, so one thing that's important to understand here, let me switch back to my slides, is that the plot file, or the data that goes into the plot file, is processed before saving. So for nodal variables, there is little to no processing going on. So for example, displacement or other primary variables that FEBio solves for, they are stored directly unprocessed into the plot file. Element variables, on the other hand, and surface variables like stress and contact pressures, they are processed before they are stored in the plot file. And the reason is because FEBio evaluates these variables at the integration points to evaluate the residual and the stiffness evaluation. So those are the only points at which these variables are really get evaluated. But we cannot store the integration point values directly into the plot file. And this is again for practical reasons, because otherwise the plot file would grow quite a lot. So instead, these integration point values are processed. They can be averaged or projected onto the nodes of the element before they are stored in the plot file. And so there's three data formats that we are currently using to store these processed data values. So on the figures below here, I'm trying to illustrate the three different scenarios. So in option A, basically the integration point values are averaged and you get a single value per element. So in the graph below, in the 1D equivalent, you kind of see that which kind of represents an interpolating function of that data, would represent here a constant value per element. In option B, the integration point values are projected to the element nodes, and then the nodal values are averaged from all the elements sharing the node to obtain one value per node. So that's referred to as the nodal formats. And again, you can look at figure B here to kind of see what's going on. And if you look at the 1D equivalent, you see that this basically gives you a function that has the same value at each of the nodes. So that is continuous at the nodes. Option C is where the integration values are also projected to the element nodes, but in this case, there is no averaging going on, so those nodal values are stored directly for each element into the plot file. So I'm referring here to figure C. And if you look at the equivalent 1D representation, so the interpolating function would look like that. So you can have variation within the element and not necessarily continuity over the element, on the element boundaries. Okay, so historically we've used this item format, so basically the element average format for all of the element and face variables. But recently we've started exploring some alternative representations that are more accurate in certain situations. And so you will find often nodal equivalence. So there is a stress, but there's also a nodal stress. There's a contact pressure. There's also a nodal contact pressure that uses one of these other two data formats. So how do you know the data format that is being used? Well, if you go to your, let's see here. Let me go to the plot file. If you go to the data panel, there is a column here that specifies the format for all of the data variables that are being used. And as you can see here, I'm just using the default values of item, which means one value per item, which can be an element or a facet. So let's take a look at the stress here, and I'm going to turn off the top one. Now, even though the data comes in as one value per element, it's still being represented here as a smoothed variable. And so the reason why that is because FEBio itself does an additional smoothing operation. So it's in order to create a continuous representation of the data, it does an additional averaging. So it basically averages all the element values around a particular node. So you can turn that off, and sometimes it's important to do that so you can actually see the raw data that comes into FEBio Studio. And so to turn that off, you would go to the color map item and turn off the nodal smoothing option. Okay, so this shows the data more closely to how it actually is represented in the FEBio Studio file. So let me show one more example here of what a nodal variable would look like. So let me add that nodal stress. Wait, let me just run this again. So the nodal stress uses that mixed data format that I talked about. So it actually projects the nodes from the integration points to the nodes. Where'd it go? Nodal stress. So if we now turn off the nodal smoothing option, we'll see that we basically get a variation across the element, but it's not necessarily continuous across the element boundary. So the reason why we start adding these different formats for stresses and things like that is because we noticed that especially for higher order elements, the traditional way of averaging integration values is actually not giving a very accurate representation of the stress. So in a later webinar, when we talk more about higher order elements, we'll explain this a little bit more and show you what kind of stress measures you should be using for higher order elements. Okay, so with that out of the way, let's jump into contact. So first of all, what is contact? And contact is basically any mechanical interaction that requires between different parts, and in this case, this webinar, we're focusing on the contact interfaces where surfaces of different parts making physical contact with each other. It's important to understand that FEBio does not detect contact automatically, and there's a couple of good reasons for that. So the first reason is that adding contact can be very costly in terms of computing time. So, if you don't need it, don't use it. But the more important reason is that there are many different contact types, as we will see, and it's not possible for FEBio to know in advance what kind of contact that you plan on using. Okay, so the bottom line is, if you want to use contact, you have to specify the contact type, and you have to define the surfaces that make or will make contact in your model. So how do you determine which contact interfaces that you want to use? Well, you can ask yourself a few questions. So the first question, and perhaps the most important question you have to ask yourself, is what are the materials that are making contact? Are they rigid? Are they elastic? Are they biphasic? So in each of these cases, you will probably use a different contact type. Another question you can ask yourself is, well, should the contacting surfaces slide across each other, or should they remain fixed? So that also is going to affect what contact type that you choose. And in the case of sliding, do you want to take friction into account or not? Okay, so we hope that by the end of this webinar, and by asking yourselves these questions, you will be able to know which contact type that you're going to use or that you need to use. So let's start with a big kind of a bird's eye overview of the different contact formulations in FEBio. So we kind of distinguish three different types. There is the rigid contact, which connects a deformable part to a rigid body. You can think of this in a way as a special case of a tight contact. So we'll talk about that more in a second. The second category is tight contact, where you have two non-conforming meshes. So for instance, you have a coarse mesh on one side and a finer mesh on the other side, and you want the two surfaces that contact, you want to make them move as one. So that would be a good application of a tight contact. Right? So the point is that there is no relative motion between contacting surfaces. The third contact type is sliding contact, which allows the surfaces to make contact and to slide across each other. Surfaces can also separate, but they cannot penetrate each other. So what we'll do in the next few slides is talk a little bit more in detail about these different contact types and show some examples in FEBio Studio. So the first contact type is rigid contact. And the reason why this is a bit of a special contact formulation is because FEBio handles rigid bodies in a very particular way, right? It does not assign nodal degrees of freedom to the nodes of a rigid body. Instead, all of the degrees of freedom that are attached to a rigid body are basically eliminated and replaced by the 6 degrees of freedom of the rigid body. So what happens when you use rigid contact, you're basically assigning the nodes of a deformable mesh to that rigid body. And so those nodes will now also be considered part of the rigid body, meaning that the corresponding nodal degrees of freedom will be eliminated. And so this is a very efficient way of tying a deformable part to a rigid body, right? So in principle, you could use a tight interface, as I'll show later, but if one of the parts is a rigid body, then the rigid contact is the way to go. Again, this is only for making a tight interface. If you want a deformable part to slide over a rigid part, you will need a sliding interface. So this is often done to apply a particular force or moment or displacement or rotation to a deformable part surface. So for instance, if you want to load a model given some experimentally determined force, if you without a rigid body, it's not clear how that force really needs to be transferred to the deformable part. So one way of handling that is just making a rigid body, applying the force to the rigid body, and then using a rigid contact to connect the rigid part to the deformable part. This is the only contact formulation where you do not require a mesh for both sides of the contacting site. And so we'll talk about that in a second here when we show an example. Excuse me. Okay. So by the way, the examples here that I'm showing are available on the repository. So there's a new item here called webinars, and so the webinar contact modeling contains all the files, including an example project file that you can look at if you want to take a look at these files yourself. So let's open the rigid contact, and we'll start the one with the geometry here. Okay, so what we're doing in this example is we have a deformable part, which is the orange part, and we have a rigid part, which is the yellow part. You can look at the materials here. So the deformable part is Neo-Hookean, the rigid part is a rigid body. The left side of this deformable part is fully fixed, and the rigid body has a prescribed rotation around the x-axis. So in order to connect the rigid part to the deformable part, we have to use a rigid contact. And so I already set this up, but let me delete this so I can show you how to actually set that up. So to add a contact interface, and this will be the same for all the contact interfaces, you can either go to Physics, Add Contact, or you can right-click on the contact item in the model tree and click on Add Contact Interface. So this shows the dialog box that has all the contact interfaces, at least relevant to structural mechanics. And so we'll talk about the other ones later, but we'll start here with our rigid contact formulation. To define the rigid contact, we have to select the rigid body or the rigid material that represent the rigid body. And then we also need to assign a surface to that rigid interface. So the surface I want to assign is the right side of this box, of the orange part. So to make it a little bit easier to select that, I'm going to hide that part by selecting it and then clicking the H shortcut key. So that gives me a clear view of that surface. I can select that surface now and assign that to the rigid body, to the rigid contact interface, yeah. Okay, so that's it. So it's fairly easy. And now this right side will be considered part of that rigid body and move with it. So let's solve that quickly. It should only take a minute or less than a minute. Okay, and here you can see that indeed the deformable part now twists along with the rigid body. So as I mentioned, you actually don't need a rigid body, and there is another example here that shows this. It's the same problem, but it doesn't have any geometry for the rigid body, right? So, so let me correct myself here. So you do need a rigid body, but you don't need any geometry for the rigid body. So this model will run exactly the same as the previous one, even though we don't have any geometry for the rigid body. Okay, that's really all that needs to be said about rigid contacts. Fairly easy to use and fairly easy to set up. So let's focus now on the other contact interfaces, being tight and sliding. Now, because there's a lot of common terminology between these two these contact types, we'll start by explaining some of the basic terminology here. To begin with, well, there's obviously going to be two contacting surfaces involved. One is called the primary surface. The other one is referred to as the secondary surface. And the primary surface is the one where most of the contact calculations are done on. So what does that mean? So in order to calculate the equivalent nodal contact force, we have to do integrations over the contact facets. And so all these integrations are done on the primary surface. The secondary surface, the main purpose of that surface is really to determine which points of the primary surface are in contact. So a question we often get is, does it matter which surface you pick as the primary or secondary? And the answer is yes. So the general recommendation is to pick the finer, non-rigid surface as the primary surface. So you want to pick the finer because that will give you the most accurate evaluation of these contact nodal forces. However, there is some issues if that surface is rigid, especially when you use the auto penalty feature, which I'll talk about later. So in general, pick the finer non-rigid surface as the primary surface. Okay, now in order to figure out if nodes are in contact, the nodes of the primary surface are projected onto the secondary surface. And the separation between a contact point and its projection, we call the contact gap. So that contact gap can either be a scalar value in the case of sliding contact, or it can be the vector separation, separating the point and its projection, which will be the case in the tight contact. So there's two parameters that are relevant here in this projection and that are a bit of a source of confusion. So I want to explain these two in a little bit detail here. And so the two parameters are the projection tolerance and the search radius. So the projection tolerance is probably the least of your concern, but basically what it does, it gives a little bit of a area around the facet where if a point projects a little bit outside the facet, it's still considered on that facet. And the reason is that there's this little fudge factor is because imagine a point projects, right on the edge of a facet. So it can happen that it actually, during the Newton iterations, that point will kind of flip-flop between different facets. And that's not a good thing because that, may cause convergence issues. So kind of to combat that, we there's this little fudge factor that allows the point to fall slightly outside the facets. The default value is 0.01, which basically means that points can fall about 1% of the element size outside of the facet. Now that default value works fairly well and you rarely have to change that. The other parameter is more interesting, which is the search radius. So that parameter basically determines the maximum distance to the secondary surface. So that means any facets on the secondary surface that fall outside of the search radius are not considered eligible for contact. And why this is an important parameter is because when you have very complex geometry with surfaces that curve in complex ways, it is possible that the projection can pick up incorrect facets. And the way to kind of combat that is by shrinking that search radius to make sure that that does not happen. Okay, so that's about the constraints. That's about the projection. So let's talk about the constraints itself. So contact is a nonlinear constraint, and it is enforced through a method called the Lagrange multiplier method. Now, Lagrange multiplier methods, in this case, have a physical meaning. They are essentially the tractions that are needed to enforce the contact. And the important thing to know is that FEBio does not solve directly for the Lagrange multipliers. Instead, it uses an approximation method for estimating these Lagrange multipliers. And there are two methods implemented. There is the penalty method and there is the augmented Lagrange method. So let me talk about that on the next slide here. So the penalty method, imagine that there is this little spring that connects a contact point with its projection, right? And so when that in the case of tight contact, so you want those 2 points together. So when the points separate, that spring will kind of pull these points back together. And that force that pulls these nodes back together is proportional to that gap and also proportional to a user-defined penalty factor. So the penalty factor is something that you specify in the contact as one of the contact parameters, right? And that's it. That's all that the penalty method does. And an important thing to note here is that the only way to get contact is to have a gap. So without a gap, there is no force, right? And so that means that if you use the penalty method, there will always be some gap when you deal with contact. So there are a few different ways to combating that gap and to making it as small as possible. And one way to do that is using the augmented Lagrangian methods. So in the augmented Lagrangian methods, what's going to happen is that it's going to keep the approximations to the Lagrange multipliers constant during the Noether iterations. It still has a penalty contribution to the total contact force. Once these Noether iterations converge, the Lagrange multipliers, the lambdas here, are updated using this formula, and then the time step is solved again. This time again, keeping the Lagrange multipliers constant. And so this process is repeated until these augmentations converge to a user-specified tolerance. Okay, so let's talk some specifics on the contact formulation, the tight contact formulation. So again, the contact force is determined by the vector separation between a contact point and its projection, multiplied by the user-specified penalty factor. So if I open up here an example, where is it? Tight contact, there we go. So in this case here, we have a box that's made out of two parts. And as you can see, the mesh between the two parts is not conforming. And the boundary conditions that we have here, we have a fixed boundary condition on this side, and then we have a boundary condition on this side that pulls the yellow block to the right. In this case, we have a tight contact interface. So I've already set it up, but if you need to do this yourself, what you would do is you go to Contact, right-click, Add Contact Interface, and select one of the tight contact options. So these are three different flavors of contact formulations that we have in FEBio. And the main difference between these are how that the projections are being calculated and which contact points that they're using for the projection. So the oldest one, and the first one we implemented, was just the tight node on facet. It projects the nodes of the primary surface onto the secondary surface using a closest point projection. This formulation is inherently symmetric. The second formulation we implemented uses the integration points instead of the nodes of the surface and projects those to the secondary surface as also still using the closest point projection. And the reason why we use the integration points is because that gives us a much more accurate sampling of the contact interface. The most recent one that we implemented is a tight elastic interface. So in this case, also the integration points are used, but instead of a closest point projection, we use a normal projection. And the reason why we do that is because it turns out the closest point projection does not always give one closest point. So you can have multiple points in your mesh that are equidistant to a contact point. The normal projection, on the other hand, always gives a unique intersection with the secondary surface. And as we've noted, that often gives better convergence and stability of your contact model. One thing to point out, though, is that this formulation is inherently non-symmetric, although it does have an option to use a symmetric stiffness. However, we notice that it often runs better if you use the non-symmetric formulation. So let's take a quick look here. So in this case, we are using a tight elastic interface. And let me first set things up using the default parameters. So the default parameters that you get is not using augmented Lagrangian, penalty factor of 1, no auto penalty, which I'll explain in a second. And that's it. So let's see what happens when we run this model. So we see here that with the default settings, we get quite a big gap between the two parts. And so this is something that you'll probably run into quite often. And so how do you combat that? Well, to combat that, the first thing you can do is increase the penalty factor. Let's say 100. So if we change this to 100, we already get a much better enforcement of this contact. Now, the problem with playing with the penalty factor itself is that the penalty factor has units, right? It's basically force over length. And so it can take a little bit of time to finding a good penalty factor yourself that works for your particular model. So to help with that, there is a feature called the auto penalty parameter. And if you turn that on, and usually I would recommend turning that on, what FEBio is going to do is it's going to basically estimate an initial guess of the penalty parameter based on the stiffness and the element size, so that you don't have to play that much with the penalty factor. Now, in this case, you still can change the penalty factor. In this case, the penalty factor simply will become a scale factor to the auto penalty parameter. Okay, so if we use that, you'll see that we'll already get a much better enforcement than the initial attempt with a penalty factor of 1. And to make it even better, what we can do is we can turn on the augmentations. And in this case, I like to do 2 or 3 minimum number of augmentations. So now it's going to solve each time step multiple times, cranking up that Lagrange multiplier in every iteration until it converges. I forgot to turn on the symmetry flag, and hopefully this will run. Okay, perfect. And here we see we have, even though the penalty factor is 1, we have very good enforcement of the contact. So let me restart the presentation here. Again, my apologies for this technical issue. Okay, so I kind of talked about these parameters here. So let's skip here to the next slide. So this slide kind of summarizes the effect of changing these different parameters. So the blue curve, the penalty only, you can see that you need to go to a pretty high penalty to get good contact enforcement. Whereas if you use auto penalty, and then especially with the augmentation, you can get pretty good enforcement of the contact, even with a small penalty parameter. So one thing to point out is that we actually do have a true Lagrange multiplier formulation in FEBio. So if you use the tide node on facets, there is an option to use a true Lagrange multiplier formulation. So in that case, FEBio will solve directly for the Lagrange multipliers. And the advantages here is that you get pretty much exact enforcement of the contact constraint. You don't have to worry about penalties or augmentations or anything like that. The downside is that because these Lagrange multipliers are now added to the global system of equation, you do get bigger systems of equation that you have to solve for. And so they can take a little bit longer to solve. So there is an example in the project file that you can look at if you're interested. But let's move on to sliding contact. So in sliding contact, what we're trying to do is we're trying to prevent the contact points from penetrating the secondary surface. So the points cannot penetrate the surface, but they can slide across the surface, and they can still obviously also separate from the secondary surface. In this case, the contact gap is a scalar quantity. It's a signed scalar quantity, meaning that it is positive when the node is not in contact, and it is negative when the point is considered in contact. So in this case, the contact force is proportional to the local normal multiplied by that gap, and then multiplied by the user-defined penalty parameter. Okay, so some of the contact formulations support friction, namely the sliding elastic and the sliding node on facet. So If we go here to the sliding example, so in this sliding example, what we have is we have a rigid body. Sorry, it's a neo-hooking material, but it's fairly stiff, which slides over a softer neo-hooking material. Let me actually just show you what's happening here. Okay, so it gets pushed down and then it slides across the deformable part. So how do you set that up? Well, the process is the same. You would add the contact interface. In this case, you would choose one of the sliding elastic formulations. And again, there is three different flavors here. The differences are the same as before. So the sliding node on facet projects the nodes to the secondary surface using a closest point projection. The facet on facet projects the integration points from the primary surface to the secondary surface, again using a closest point projection. And then the sliding elastic formulation projects also the integration points to the secondary surface, but in this case uses a normal projection. So again, important to point out that the sliding elastic formulation is inherently non-symmetric. So it has the option to use the symmetry flag, but if you see any convergence issues, the first thing to do is turn on the non-symmetric formulation flag. So most of the parameters for the sliding contact are the same as for the tight contact. There's a couple additional parameters that are worth pointing out. And the first parameter is the seg-up parameter, or the number of segment updates. So during the Newton iterations, what can happen is a point from the primary surface gets projected to different facets on the secondary surface as the Newton iterations kind of update the mesh. So just like we had the projection tolerance initially, this can also happen with larger displacements. So it doesn't have to be just on the edge of an element. Nodes can kind of flip-flop between different facets on the secondary surface during the Newton iterations. And that is problematic because every time a node switches to a different facet, the force distribution is a little bit different. That affects the residual, and it can happen that the residual simply cannot converge because of this flip-flopping. So because of that, you can set a maximum number of these segment updates. For instance, 3 or 4 is usually enough. And so basically that means that after that 3 or 4 segment updates, that node is no longer able to project to another facet. So that can add some stability to your model. The other parameter that I want to point out is the two-pass parameter. So I mentioned earlier that it is important that you pick or which surface you pick as the primary or secondary surface. Now, because it matters, it actually adds a little bit of bias to your model. Right? Imagine you have two surfaces that are somewhat similar in density, so it might not be obvious which one you pick as the primary, which one you pick as the secondary. But regardless which one you pick, you might get a slightly different answer. And so you are introducing some bias to your model. So one way to combat that is by turning on the two-pass flag. In that case, the contact algorithm will be processed twice, the second time with the primary and secondary surfaces switched. So in that case, it doesn't matter anymore which one you pick as the primary or secondary, because both surfaces will be considered as primary or secondary in the second pass. And then the final parameter I want to point out is the friction coefficient, which is supported for the sliding node to facet and the sliding elastic contact interface. Okay, so before we do this, let me talk a little bit more about setting this up, and let's play a little bit with the parameters here. So in this case, we chose a tight elastic, or a sliding elastic, sorry, sliding elastic contact interface. And let's start by lowering, well, let's see what kind of results are we getting here. So this actually already looks pretty good. So instead what I'll do, let me talk about how can you verify how good your contact is enforced after you run the model. And so this goes back to the earlier thing we talked about with plot variables. So when you work with contact, it's important to check which variables that are stored to the plot file. FEBio Studio, as of now, does not add any contact plot variables by default, so it is important that you check that, and then you add these plot variables yourself. So the way to do that is, again, go to Output, select the plot file. You can right-click on that, or you can just click the button here, Edit Plot Variables. So the Edit Output dialog opens up, and again, you can use the filter to find all the contact related parameters. So the ones of interest are the contact gap, which will tell you how well the contact is enforced, and then the contact pressure, as that will give you an indication of the force or the traction. In fact, if you're using tractions, you might be more interested in the contact traction instead of the contact pressure. But since this is a sliding elastic problem, we'll just use, we'll use the contact pressure. Okay, so you can see on our data panel here that the contact gap is here, as well as the contact pressure. So the format by default is the item, which, remember, means that the integration point values are averaged over each facet before they're stored in the plot file. Okay, so let's take a look at the contact gap. Turn off the top material here. So we can see that the contact gap is indeed fairly small, so the contact is fairly well enforced using the contact settings that we've used. Another useful way of kind of looking at overlap is by using a plane cut. So you can use a plane cut to kind of see how well your contact is being enforced. And you can see that there's still a little overlap here in the corners on both sides. So if you want, you could try increasing the penalty factor, or you could turn on augmentations or something like that. Okay. So I talked about the contact plot variables. Again, I remind you, right now, FEBio Studio does not add these contact variables by default. So please make sure that you check these plot variables before you run your models. So, so that kind of covers the basics of contact. So hopefully that will give you a basic idea of, the theoretical foundations of the contact formulations in FEBio. So in future webinars, we'll talk about some more advanced scenarios and problems you could run into. But I wanted to add this one in this webinar because I feel this is something that people often run into when they try to do force-driven contact problems. So imagine here, there's a schematic here of a bone or two bones that have a soft tissue layer on top of them that are about to make contact. And the top bone, so the bottom bone is fully fixed, but the top bone has a force supply and is otherwise unconstrained. So you might think that the contact is going to catch that top bone after you apply that force, but in reality, that's not what happens. So if there's an initial gap separating the two contacting interfaces, then without any other constraints to the top bone, this problem is ill-posed. You can kind of understand that by thinking that the contact is always kind of a step behind. Like the contact doesn't actually engage until there is actual overlap. So in the very first iteration, what happens is, well, that force is being applied and there's nothing stopping that force. So that means that the displacement of that bone is going to be infinite in theory. In practice, because of numerical roundoff error, it will be a value, a finite value, but it will be very large. So there will be a very huge penetration into the second bone. At that point, it's just too late for the contact to do anything about that. Now, fortunately, there's two ways you can get around this issue. The first way is to allow a small initial overlap so that the contact is engaged in the very first iteration. And the second approach is by using a two-step analysis, where in the first step, you apply a displacement on the top part here until contact is established, and then in the second step, you apply the force. So I want to demonstrate these two scenarios quickly here. So in the project file, the first one is the contact force. Okay, so what we have here is we have a rigid body. It's this purple icon here. And then we have two deformable parts that are making contact. The bottom part is fixed on the bottom, and the top part is tied to the rigid body using a rigid interface here. And then the rigid body has a force applied in the z direction. Okay, so let me first show what happens if I allow an initial gap. Right, so in this case, so there's an initial gap here. Force is being applied to the rigid body. There is nothing stopping that force or counteracting that force. And so when you try that, you will see indeed you get an error termination. So the first solution was make sure there is a little bit of overlap between the primary and the secondary surface. It doesn't have to be much, just enough for the contact to engage. If we run that now, you'll see that the model indeed runs perfectly fine. The second approach is using the two-step analysis. So in this case, we keep the initial gap, but our analysis now consists of two steps: a displacement step, where we are applying a fixed displacement. So the separation here is 0.3. And so we're going a little bit further, 0.31, just to engage that contact. And then in the second step, we apply the force. Now there is another problem that arises here. So after the end of the first step, the contact is engaged very well. So it's pushing back on the primary surface, or on the orange part here. But now if you start the second step with the applied force at 0, well, then you're back in the same problem as before, except now that the contact is applying a force to the model and there is no force yet counteracting that model. So if you start your rigid force at 0, then what's going to happen is the contact is just going to push the primary surface away and you're back where you started. So in order to address that, you want to be able to start at whatever force happens to be applied at the end of that displacement step. And fortunately, that's easy to do. So you just have to change the load type here from load, which is the default, to target. So if you change that to target, what's going to happen is that the initial value of that force will be whatever reaction force that is being applied on that rigid body as a result of, in this case, the contact. And then FEBio will simply ramp up the value to the target value here of -10. There is no load curve involved here. So if you look, if I open up the curve editor here, oops, it ended up on my other screen here. See, there's no curve no load curve here associated with that force, so FEBio will automatically ramp up that value. So when you run this analysis, you'll see that this will work. This will work very well. Okay, you see that the first displacement step runs, engages the contact, and then the force is being applied. So you can look at that force actually if you go to post new graph. We select the rigid body as the source here. And if we look at the z-force, we see that indeed we have initially no force on the rigid body during the displacement step until the very last moment where the contact engages. So the displacement step results in a reaction force, a small reaction force on the rigid body. And then the second step starts from that value and simply ramps up the force to the value that we want it to have. Okay, let me switch back to the presentation. So I hope that gives you an idea how to deal with this common problem of force-driven contact. So in future, as I said, future webinars will address some other contacts issues like self-contact, higher order element contacts, and so forth. By the way, we'll have a short review at the end of this webinar that we hope that you can answer that. And if you have any suggestions for future topics, not just related to contact, but anything else, we would love to hear from you on that. So that, that survey will be shown at the end of the webinar. And you'll also get an email. If you don't have time to do it now, that's fine. You'll get an email about this. But again, we really appreciate it if you would take the time to fill out that survey. It shouldn't take more than a minute to do so. Okay, so that kind of brings us to the end of the presentation. So we'll leave the Q&A session open for another 10 minutes or so before we wrap things up. So let me take a look here at the question window. So the other panelists, if they want to talk to answer these questions instead of typing them in, if that would be easier. Okay, so I have a question here. Could you comment on selecting a surface versus a set of facets for a sliding contact? So that's a good question that I didn't point out, but what can you assign to a surface or to a contact? So in this case, I only showed boxes and simple geometries, which happen to be partitioned in ways that allow me to simply select the geometries, the surfaces on the geometry. But in more complex situations, that is not possible. So instead, you can select the facets of a surface and assign that directly to the contact interface. So let's say if I don't have this here, and by the way, I want to point out here this relatively new option where you can clear the selection entirely. So if you didn't want to make this a surface selection, you can just click on that. That removes that selection entirely, and then you can change that to a facet selection. So now I have 100 facets assigned to the secondary surface. You can combine both, so you can have a surface, a geometry surface for the primary, and facets for the secondary. Okay. Is there a way to visualize where my model is failing, where negative Jacobians are detected? Yes, there is. There's a couple different ways. So So right now, by default, what FEBio does, it just reports that there's a negative Jacobian and then retries the step again. But sometimes the model will fail because it can't get past that negative Jacobian. So what you can do is there is a flag in the configuration file that you can set so that FEBio will print out all the integration points of all the elements where a negative Jacobian was detected. So that used to be the default, but because often a lot of elements invert, and so just printing all these elements for a large model took an insane amount of time, and so we turned off that option. But if you want to have that option on, it's still a setting that you can set in the configuration file. The other thing you can do is you can run your model in debug mode. So if you run your model in debug mode, what's going to happen is that FEBio is going to store all the non-converged states, including the ones that generated the negative Jacobians, to the plot file. So you can then, after the model fails, you can open the model in the plot file of the model in FEBio Studio and then visually see which elements are being inverted. And I want to add to that there is a new feature here. If you add -G2, the model will run just as normal, but if a negative Jacobian happens, it will store that state to the plot file as well, right? So usually when you run a model and it hits a negative Jacobian that it cannot solve, the FEBio will stop. But if you add that G2, it will also store that state to that inverted state to the model file. Right? And this is perhaps a better option than the -G, because the -G adds all the model states to the plot file, so you can end up with a really large plot file, right? So try the -G2 as an alternative to that. Okay, so any other questions? Check the time here quickly. Okay.
There was a question that I answered about modeling articular cartilage attached onto bones. Someone was interested in knowing how you would use the different contact algorithms. So I just thought I'd elaborate on that. So oftentimes, we have maybe two bones and articular cartilage on each end of each bone, and we model those two articular layers coming into contact. So the first thing I think we usually ask ourselves is whether it's reasonable to model the bones as rigid. In other words, relative to what you're interested in, is that a reasonable assumption? And if it is, that's always something that we try to do if we can get away with it. And so as we discussed, if you model the bones as rigid, instead of having all those degrees of freedom for whatever discretization that you've used for the bones, some sort of solid elements presumably, you only have the 6 degrees of freedom. And so then there's this question of how to attach the articular cartilage onto the bones. And there are really two options here, whether it's rigid or, well, if it's a rigid bone, you can either have a conforming mesh and merge the nodes between the two, but oftentimes the mesh that we have for the articular cartilage, the nodes of that mesh don't conform with the bone. And that's where the rigid contact comes in. It makes it really simple to attach the cartilage layer onto the bone. And Steve went through this example and showed how to do that. You're still left with the contact between the two articular layers. So that's going to be another contact interface that you would specify. And since both of those layers are deformable materials, you would use a contact interface that allows for sliding and separation. One of the 3 options that Steve talked about for elastic materials. So hopefully that clarifies how you can go about setting up our musculoskeletal or diarthroidal joint contact problems with the different interfaces that are in FEBio. Now, if your articular layers are modeled as, for instance, biphasic materials, and you want to be able to take into account the potential flux of fluid between the layers, then there's another type of biphasic contact interface in FEBio that's appropriate to use. And we'll cover that in the next contact webinar that we do that will extend on what we've covered today.
So I wanted to quickly point something out that someone mentioned during the webinar, Steve showed you the model repository project containing the example files for this webinar. Unfortunately, it appears that there is a problem with those files in the repository and they are not downloading properly. I think that I've identified the issue with this, and hopefully later on today, those should be available for download, but right now you won't be able to download them.
Okay, thanks, Michael. Okay, so let's take a look at the time here. We could probably take one or two more questions. So I saw a question earlier on contact with Shell. So it looks like Gerard answered that question, but I want to add to that this is something that we'll probably discuss in a future webinar because there are some challenges when you use shell elements in more complex geometries. So you know, we'll breach this topic in a future webinar. So we take a look here. So any other questions? Looks like all the questions have been answered. Okay, so let me then wrap up the presentation here. Okay, so first of all, I would like to acknowledge the other members of the FEBio team. So many of them were here today answering all your questions. So thank you for doing that and being here. I also want to acknowledge our funding sources, the NIH, which has been generously funding the FEBio work for since 2009, I think. So, you know, 12 years at this point. So, of course, we're very grateful for that funding, and we hope that they will continue to fund us for many more years in the future. So if you want to know more about FEBio, then the place to be is www.febio.org. So you can go there to find all the software downloads. You can find the manuals there, so you can find tutorials there, and all of those are available in the knowledge base. So you just go to the main page and then just click that knowledge base tab on the top. So you can also find a link there on the forum. Actually, the link is under the support tab, if I'm not mistaken. So on the forum, you can ask questions related to FEBio and FEBio Studio and reach out to the community in general. You know, we as developers also monitor that forum daily and try to answer as many of the questions as we can. So any other questions, you can ask us by sending us an email. So the best way to reach us is by emailing info@febio.org. So I also want to remind you that the FEBio and FEBio Studio software are all open source. So you can just go to github.com/FEBio software to find the source code of the software. If you want to stay up to date on recent news and announcements, follow us on Twitter. Our Twitter handle is @FEBio Software. And then also check out the FEBio videos channel on YouTube. In fact, this webinar will be posted there as well. The previous webinar, the Intro to FEBio Studio, is already available there. So if you want to have a more introductory presentation on FEBio Studio, I suggest to check out that video. So with that said, I would like to thank the audience for participating in this webinar. I hope that you found it informative and can use a lot of this material in your contact modeling. So thanks again for participating, and I hope to see you again in the next webinar. Bye.